All right, hello guys. This is Monsak Sojulantam, a researcher at NECTEC, National Electronics and Computer Technology Center, Thailand. This presentation is made based on my experience on reviewing technical papers on GNSS and also technical documents, including the International GNSS workshop held in Beijing, China on Beidou. Beidou is a Chinese GNSS systems. So I would like to make this presentation to share the knowledge on the current situation of GNSS implementation by the powerful countries and how it is affecting the Asia Pacific countries. Let's start. GNSS stands for Global Navigation Satellite Systems. As you can see, it's a system, satellite systems for navigation, and the global means it's cover the whole world, the whole Earth. So it can be used anywhere to locate a receiver positions. History of GNSS, just some part to get you some idea. 1960, the first navigation satellites called Transit launched by the US. And in 67, the US launched another satellite called Time. And they try to add atomic clock into the satellite so that they can measure time very much more accurate. Time is very important here because the GNSS use travel time of the signal, the electromagnetic signal, the travel time between the satellite and receivers, and they use this time to measure the distance because they know the speed of the signal, which is a constant, the speed of light. So they have to measure the time very accurate. That is the reason to use atomic clock. And after the trials, the US was confident and launched during 79 and 85. The US launched 11 GPS satellites to cover the whole world. After in 83, not really long from the first GPS satellite launch, Russia shoot a Korean civil airplane down, and Ronald Reagan, the president in that time, decided to open GPS for civil usage so that the airplanes can locate its locations and doesn't trespass the others skies. In 1990 and 91, Gulf War happened. The U.S. Army, which that time already used GPS receivers produced by the government. However, because of the war, they need a lot more, very much more number of receivers, and the government cannot make it on time, so they have to buy the receiver from the private company in the US. But one limitation is that during that time, the US government intended to add a random error into the signal called SA, selective availabilities, so that the private receivers cannot decode the information very accurately, and the positioning error at that time is around 100 meters. If the SA is removed from 100 meters, the accuracy can be just 10 meters. This is nowadays accuracy. So during the war, the US government have to remove the SA just for temporary, so that the receiver from the private can be used. In 82, the Russia launched its first GNSS satellites called GLONASS. And 2011, first two Galileo EU were launched. The EU can see the great opportunities of using GNSS, but they are the first group who pay very special interest on the economics instead of army uses. like the Russia and the US used before. In 2012 until present, China, India, and Japan are launching their own GNSS satellites and promote their system. In this presentation, I will stress on China and Japan because they are the two big countries influencing Asia Pacific regions. And you see that why I uh, choose this regions later will be more information will be show up. This is one of another reason. As you can see, the points the points represent the satellite location surrounding the areas. As you can see, this is Asia Pacific regions, and here is the US, North America, and South America. The deep red, refer to more number of satellites. It's around 35. So you see that Asia Pacific region is a very hot area for GNSS. Much more numbers of satellites will be available. This is the prediction for 2020. And all the constellation are show up over here. We also have Espace satellite, which I will mention later in detail in a slide. It also create a very high impact on the GNSS communities. Here, this picture is a good one. It is showing several interesting informations. Yes, the Earth, you have Iridium, which is a communication satellite, and they use for a satellite telephone mainly. Hubble, which is a space telescope. ISS is an International Space Station, which is very close to the Earth's surface. GNSS satellite or constellation, they are located, their orbital period is around 10 to 15 hours. And for the height, they are around 20 something kilometers above the sea level. Compass is the previous name of the Beidou, the Chinese GNSS. Let me show you this, or let me pause a little bit. All right, let's come back to the presentation. Here's the animation developed by NASA. As you can see here, you can this the satellites, all types of satellites, communication satellites, rest, all the satellite available. Over here, I am just select the GPS operational. Then you see, let me zoom out. The center is the, you can visualize the satellite orbiting the Earth. And if and select the satellite over here, satellite number that you're interested. It is moving. The numbers is keep changing, meaning they are. All right, let's come back to the presentation. Here is another animation. This is quite useful. Let me show you a little bit. This is about medium Earth orbit, GPS medium Earth orbits. So all the GPS satellites are orbiting the Earth. You can see the circle, the orbits are in ellipticals, and the orbiting planes is has around make around 55 degrees with the Earth plane, the Earth axis. and they have, by having multiple planes, you can have at least, in theory, you should have at any location on Earth, you have at least 4 satellites at a time. On Earth, you see on Earth, on the Earth surface, you see the satellite just rise, arise, and fall, just like the sun and moon. It just come up and go down. Let me go back. Uh, Now here's the Chinese satellite. I just show you the animations. The GPS satellite, including GLONASS, GPS, GLONASS, and Galileo. Of these 3 constellations, they just have only medium Earth orbit, or called MEO, medium Earth orbit. Medium meaning that those satellites are just orbiting around Earth and visiting all the location on Earth. But for the Chinese and Japanese, they have special orbits. They have combination of orbits. In these pictures, for those curves like this, like a sine wave, this represent the medium Earth orbit track. On Earth, this is called ground track. On Earth, you see the track like a sine wave. Or let me turn this off. They have MEO, the same like GPS, and they also have IGSO, inclined geosynchronous orbit. IGSO, inclined geosynchronous orbit. It syncs with the geo. Geo is the Earth. Sync with the Earth. It's rotate with the Earth, but it's because of the orbital plane is inclined. This inclination makes a number 8 shape on the region of interest, in this case the Asia Pacific. The reason why they make this kind of orbit because they want the satellites to just locate and provide the service to only the region, this region, so that more numbers of satellites visiting the region. Furthermore, they also have the geostationary satellites. Right now we have 1, 2, 3 behind, 4, 5 geostationary satellites serving the region as well. So this is the reason why the Asia Pacific region has very much more numbers of satellites than the US. So far I mentioned several technical terms about orbits: the medium Earth orbit, geostationary orbit, inclined geosynchronous orbit, and highly elliptical orbit. This is a new one, belongs to the Japanese, which I will show you in detail later. But let me show you the animations explaining more on these orbits. Somebody has done this on the YouTube, so that I just use it. The white one, it represents the geostationary orbits. The green one represents the MEO, medium Earth orbit. The red one represents the LEO, low Earth orbit. The blue is the HEO, highly elliptical. You see, the geostationary is the farthest, the LEO is the closest, and here is the GNSS. Most of the GNSS is on the green orbits, which is GLONASS, GPS, Galileo. The Japanese is on the blue one, and the Chinese, I will show you the animation for the Chinese and Japanese in more detail. Let me go back to the presentation. Here is the Chinese, the effect of highly elliptical orbits of the Japanese. It will create unsymmetrical number 8. The small circle up here is located on the Japan area. The reason why they did this because they want the satellites called QZSS or QZS to be located on the zenith, quasi zenith, meaning almost zenith, almost on your head, almost, so that they can have the signal very easy, no blocking, no reflections. But the Chinese one have the symmetrical number 8 because they didn't make it shift. You see in this animation. Here is the geostationary satellites just orbiting with the Earth. Now they are going to uh, have the inclination on the orbit, you see, and then if you create number 8, symmetrical number 8, and the GO then become IGSO, inclined geosynchronous orbit. You can see the number 8. Now it is symmetrical. If you just make it inclined, it creates symmetrical number 8. And here, this is the Chinese one. And then the Japanese, they shift the orbit up, shift it up to make the unsymmetrical number 8, so that the upper part cover the Japan, and make quasi zenith satellite or QZSS. All right, let me go back to the presentation. So here's the plan. Here's the plan of the QZSS satellite, the Japanese one. They're going to have Espace service in 2023, and by 2028 they will have 4 satellites, 4 GNSS satellites, 3 IGSO, and 1 geostationary, and they have provide service along up to 2023. During this period, between 18 and 23, they will add 3 more satellites. 2 of them are geostationary and provide the S-bus service for the Asia Pacific area. Why I keep mentioning S-bus? You see later is very important for GNSS. It enhances the positioning accuracy so much. Before that, let me check the Chinese plan first. The Chinese is participating the international standard, the S-bus standard. They also focus on S-bus in ICAO, in IWG, which international organization on aerospace and space policy. They launched in 2018. They plan to launch the first BDS base, which is BDS is a Chinese brand. BDS base, which is GEO satellite. 2020 finished the launch of 3 GEOs and provide the S-base service for China and surrounding areas. 2025 provide augmentation service, which is S-base for larger areas, meaning the Asia Pacific one. Now let us discuss the S-bus. Before, S-bus help you reduce the error and improve the positioning accuracy. But how they did it? There are the major source. There are 3 major sources, which is the reflected signal, or somebody call multipart. And the second one is obstructed. The signal doesn't reach the receiver. The third one is the refracted. As you can see, the signal doesn't go in the straight line. The first 2 The first two we are not able to remove because it depends on the local environment. You cannot just remove the obstruction. But the third one, the refracted one, it is possible to calculate how much it reflected, and then share this information to the receiver on Earth so that they can make compensation on the measurement and improve the positioning accuracy. Here is how it works for Espace. You will need, the government or somebody, a central body, need to set up a reference station fixed in under open sky and just keep observing the GNSS satellite 24/7. Transfer this raw data to a master station. The master station calculate the correction information and then upload it to the satellite. We call it Espace satellites. Then the satellite broadcasts this correction information down to the receiver on Earth. And at the receivers, they observe the GNSS and the S-band, combine the correction information into the positioning calculation, and this results in sub-meter accuracy, so that the normal 10 meters accuracy come down to 1 meters, and which is around 10 times better. Here is the existing S-bars in the world, which is EGNOS in Europe, Gargan in India, MSAS in Japan, and the WAS in the US, all in black. The gray are still underdeveloped. In Thailand, most all of these S-bars, they are designed and launched, implement just to serve the countries like for Japan. When they launched, they aim to serve Japan, the US and India also. They just mainly serve the country. However, a neighbor country like Thailand, which is close to India and Japan, we can still receive the signal. And as I tested in Thailand, I use the signal to correct my position, and I found that it helped me improve the accuracy from around 10 meters to around 1.9 meters, which is much better. So even if they are far away and they are not specifically designed for Thailand, because the atmospheric conditions are still similar, so that the correction information is still be useful. Here is the GNSS view and simulation. It's a website developed by the Japanese, and they also have the app on iPhone and Android, which you can search for GNSS view. Let me show you the application. For here, you can select any region that you want. In this case, I use Southeast Asia, and the city, any city, or you just say the latitude, longitude that you want to see, the time that you want, the masking angle, and the satellite constellation that you would like to see. In this case, GNSS, GPS, GLONASS, Beidou, Chinese, the Galileo, Europe, and the Espace. I think my internet connection is not good. Okay, it's come up. Thanks God. Right now I check S-bars, and you can see because they are stationary, so even if I move, the satellite doesn't move that much. But if you are interested in like Beidou, the Chinese, let's see. Oh, that's a lot. 12 visible satellite, 12. And you can move the time scales to see how the satellite moves during the day. You can do it until 2017, and you can go back in the past too to see how satellite is. Okay, let's go back to this presentation. Here is the Chinese. Recently, just last month, June 2016, they just announced a official white paper by the government. How is this important? In the past, the Chinese government never officially announced or commit any policy related to GNSS. But just last month, June 2016, they just officially announced by the government. If you read the document, it only the key main idea are four words: independence, openness, compatibilities, and gradualness. Independence mean they plan to independently provide satellite navigation services to global users. This, if you can see, I think this high a political meaning behind independently provide. And openness, they provide the service free of charge. Compatibilities, they plan to have interoperability with other navigation satellite systems. They don't to just focus on their own satellite system, which is good. And gradualness, meaning they develop the BDS, the Chinese project, step by step. In the past, they started from just Chinese area satellite. They launched just one or two satellites. And then the second phase, they focus on regional, which is Asia Pacific. And that phase is just done. Next, by 2020, they plan to have the full constellation covering the global by 2020. And in that time, they will have 35 satellites orbiting around the Earth. So this official white paper is very important because they just officially commit to the world community. If you want to have more technical detail about the GNSS, you can just go check interface control documents. It is important for somebody who wants to make a GNSS receivers. In the documents, we'll explain in detail about the frequency they use, the data encoding, the navigation methods, structures, and format. All of the information that is necessary for making receivers and process the signal will describe in the documents. So far we discussed GNSS, more number of satellites will be available, and the Espace, more number of Espace will be available too, and that will increase the positioning accuracies around 10 times better. These two factors help a lot for several environments. For example, in this one on the left, a car is moving from here to here. They call this environment urban canyons. Urban canyons. So high-rise building are located around. So the chance is very high to have multipart or the reflections. And this reflection makes the positioning error by very large. As you can see for here, the receivers in the car thought that the signal is direct. So they thought the car is just follow the signal, just follow the direct line, and the car is here by the computation, but actually it's here. So by having more number of satellites, you can just filter the low angle satellite off and use the high angles, and you can still have enough satellites. Just like these pictures. And in some environments like in open pit mines, there is like valley. You are working in the valley and your sky are very close. You have just very small angle to see the satellite. So the GNSS, multiple GNSS is useful also for this kind of environment. In conclusion, let me just focus on the two big countries. 2018, China will launch the first Espace. Japan will have 4 GNSS satellites with 3 IGSO plus 1 GEO. 2020, China will have 3 GEOs and Espace. These 3 GEOs are just for Espace, and they will have 35 navigation satellites globally. 2023, this is a hot year. China will have S-band for Asia Pacific regions, and Japan will have operation 7 QCSS operation satellites, and also provide the S-band for Asia Pacific region. So basically, they will have at least six more S-band satellites in for the just for the Asia Pacific regions, and this impact the mass receiver, the mass users, location-based application will be affected by a lot. Foresee the impact. I cannot see all the possible application, but this just to collect. I just collect the list just to give you some ideas. The very fundamental things is the map. We will have high precision and high definition map. What that means? So far, right now, in the present, we only have single line road, digital road. We just have single line. But in the near future, we will have lanes with attributes of the lanes, like the speed limit, lane by lane, and the prohibition, lane by lane. Right now, we have footprint, only building footprint, but in the near future, we will have detailed sidewalk map and all the entrances, including attributes like the sidewalk, the slope of the sidewalks. Is there any snow or ice covering the sidewalk, something like that? So far, we don't have indoor map very widespread yet, but in the very near future, we will have detailed indoor map, and we also have indoor positioning techniques will be very widespread, which I didn't mention in this presentation, but you may search for it in Google. And the details locations of infrastructures like fire hydrants, ATM. This is just to help manage and help in navigation in some specific, in some certain requirement and application. 2D maps will become 3D and high definition map. For the application from turn-by-turn navigation, it will become lane level navigation. Okay, you take this lane is better than the other one, something like that. The traffic on this lane is better, not that much, something like that. Pedestrian navigation will be very much more better and have very much more details, because your location is around 10 times more accurate. The driver behaviors at the lane level, autonomous vehicle, of course, you need very precise positions, and widely and fully use of precision agricultures. All right, I think that's all for this presentation. I hope this is useful for you guys. Thank you. Bye bye.